So come to find out with our substitution reactions, there's two major types and they're quite distinctly different. But remember with the substitution reactions, those three basic things are going to be the same. There's going to be a nucleophile, a leaving group, and an electrophilic carbon. And during the reaction, the electrons get transferred from the nucleophile to the leaving group. But we're going to find out there's a couple of different ways that we can do this, and the difference is going to be the mechanism, how these electrons get transferred. And what we're really going to do, what's kind of interesting, is we're going to go in there and look at this transfer of electrons, and we're going to find out that this gives the two substitution reactions. So the first one's called SN2, the other one's going to be called SN1. The mechanism is going to give each one of these reactions kind of a specific difference between the two, and then we're going to combine these things together. So right now I want to warn you what we're going to do. There's going to be 4 different reactions that we talk about, and they are all linked together, and I'm going to go through each one. So if you don't see how they all tie together, don't worry about it. I'm going to do a big summary at the end. So what I'm talking about now, just worry about the individual reaction I'm talking about right now. And then as we get to the end, we'll kind of compare and contrast the different reactions. And then we'll go over a sheet that specifically answers, okay, what reaction's going on right now. So don't try to grasp the big picture at this point. Just talk about the individual reactions. So here, the first substitution reaction we're going to talk about is called the SN2 mechanism, and we'll talk about what we mean by the two. S means substitution, N means nucleophilic, and here this is kind of straightforward. This is exactly like what you would expect. So we're going back. This is a mechanism. So remember, whenever I ask for a mechanism, that means I want to see how the arrows are moving, and it gets back to our description of arrows, and arrows show the movement of electrons. So here, when we look, kind of break down what's going on, the lone pair electrons on my nucleophile are attacking my electrophilic carbon. So when lone pair electrons attack another atom, they form a bond. So this first arrow shows the formation of this oxygen-carbon bond here. Also, electrons are leaving the oxygen here. So it started off with a negative charge. If I remove electrons from it, it's going to become neutral. Over here on the other side, we're kicking off the leaving group, so we're actually breaking this carbon-chlorine bond. A bond attacking an atom turns into lone pair electrons. So in the beginning, the halogen has 3 sets of lone pair electrons. Now it has 4 sets of lone pair electrons. When we started, the the leaving group is neutral, but electrons are moving towards it. That means it's going to have a negative charge when we're done. And with the carbon, electrons are coming in and electrons are leaving, so overall it is neutral. So what's important to notice with this is this mechanism's one step. And it all happens in one step. And the two pieces that we have, the nucleophile and my electrophile or electrophilic carbon, are involved in that one step. And that's going to have an effect on the kinetics. So we're going to talk a little bit about kinetics. If it doesn't seem very familiar, you can kind of go back and review what we talked about in 115B. The kinetics is going to explain certain things about this reaction, about when will it happen or when will it not, and more importantly, why. So I'll be going over some things like rate law and rate determining steps. So if that seems kind of unfamiliar to you, you might want to go review the kinetics part of your general chemistry class. But the idea is, right now, what I want to learn from the SN2 mechanism is that because there's only one step, this must be the rate determining step. This must be determining my rate because there is only one. And in this rate determining step, my two pieces, the nucleophile and the electrophilic carbon, are involved in the mechanism. So from this, we can infer that the reaction is second order. So rate is equal to K times the concentration of my reactants. Because both of my reactants are involved in the rate determining step, they must all be involved in my rate law expression. And because there's only one of them, we're taking one nucleophile, one electrophilic carbon. That's why this is second order. There's an implied one here, implied one here. And remember, to get the overall order of a reaction, we have to add in the individual exponents. So an implied one here, one and one makes 2. So For an SN2 reaction, that's what makes it second order. So when we looked up here, that's what the 2 means. Substitution, nucleophile, second order. And so this is going to be important. It's going to have an effect on, there's going to be some effects from the fact that this is a second order reaction. So the reaction is called concerted, which means everything happens in one step. And we're going to find out as we go along that a lot of reactions happen in multiple steps, and it's going to make your life, as we get along, these mechanisms get a little bit harder. But you can see why we start with this one. It's a one-step mechanism. It's kind of the easiest one to remember. And because it's done in one step, it's called concerted. And so concerted means a lot of things happening at the same time. So like when you go to a concert, a lot of different instruments are playing at the same time. That's what we mean by concerted. So because 2 species are involved in my rate determining step, this is called bimolecular, or SN2, or bimolecular nucleophilic substitution. That's what we're saying here by SN2. And we're going to find out now, let's go in a little bit deeper, the fact that we call it second order, how does that affect things? And the first place is from an energy diagram. So same thing, we talked about energy diagrams in the 115 series. And you can kind of see why my life as a artist didn't really go so far, but we understand this. And so on the left hand side here, this is energy. So as we go up the table here, it means we become more energetic. And overall what we're doing is starting with our reactants, our electrophilic carbon, and our nucleophile, and we're making our products, in this case the alcohol and my leaving group. And notice that overall what happens is my negative charge gets transferred from my nucleophile to my leaving group, and in this case the negative charge is more stable on the leaving group, and so we are going down in energy. So in this case, the difference between the energy level of my reactants and the energy level of my products is really delta H, and that this drop means we're going in lower in energy. That means this reaction's exothermic. So there's difference in energy here. We're going down in energy. The difference in energy is being given off. Also remember, and we did talk about this in 115b, that really what determines the kinetics of a reaction is the transition state, or sometimes it's called the activated complex. So in this class, we're going to call it a transition state. And the idea is the energy it takes to go from my reactants to my transition state is called the energy of activation. So you need to put energy into a reaction to get energy out. So even though we're going from a more energetic to a less energetic state, there still is an energy barrier that we must go over. And why we're talking about this is you got to remember the energy of activation affects the kinetics. So as energy of activation goes up, the reaction becomes slower. We have a larger barrier to get through. And what we're going to be focusing about now is this transition state. So what does the transition state look like in between these 2 species? And what we're really going to be talking about is how can I stabilize or destabilize this transition state. If I destabilize it, the reaction becomes slower. If I do stabilize it, my reaction becomes faster. And so this is what we're going to be focusing on right now. We're really interested in looking at the kinetics of this reaction. So once again, delta H is the enthalpy of reaction. We're not going to talk about that so much, but it's nice to look at it. Enthalpy is the difference between my reactants and products. In this case, the reaction is exothermic. EA is the energy of activation, the barrier that we must get over to go between reactants and products. And the transition state is a theoretical high energy model. And I always like to mention this. The transition state isn't real. It's a device that we use to describe things, and we're going to be utilizing that now. It gives us an idea of what the barrier looks like to go between reactants and products, and then we can kind of theorize how can we stabilize and destabilize this transition state. But the idea is this is not real. This is just a method for us to envision what's going on and apply theory and say, what might stabilize or destabilize things in this case. So this is what the transition state looks like inside of our reaction that we're looking at, the SN2. And remember, overall what's happening is my hydroxide's coming in and it's pushing off the chlorine. So if you think about it, what's happening is during this reaction we are forming a bond between the oxygen and the carbon. The other thing that we're doing is we're breaking a bond between the carbon and my chlorine. And so that's what these little dashed line bonds mean. It's a partially formed bond. So if we take a picture at the exact halfway point between the reactants and the products, what we see is an oxygen-carbon bond in the process of being formed, a carbon-chlorine bond in the process of being broken. The other thing that happens is the negative charge gets transferred between my oxygen and my chlorine. So for a moment here, my oxygen has a partial negative charge. So the negative charge is being spread out. It's being spread between the oxygen and the chlorine. But when I take a snapshot of the halfway point, my oxygen's going to have a partial negative charge, and my chlorine's going to have a partial negative charge. So that's where the negative charge is going. So this is what it looks like, and you can kind of see where it's destable. For an instant, we actually have a violated octet. And there's some other things that we're going to look at, but the violated octet means that this is going to be a highly energetic molecule. The carbon doesn't like having 5 bonds, and so this is why it's so higher in energy. So just on the side, we will see this again a few times. When you see a bracket around something, it means that it is transitory, that this is not going to stick around. It's in the process of changing, and it's going to go to something else very quickly. And then when you see this sign, the double dagger here, this means that we're talking about a transition state. And so we'll look at a couple other transition states in a second. So one of the other things we want to remember here is that for this briefest of moments, these 3 bonds are actually in the same plane. If I was to take out this bond and just look at these 3, these are actually trigonal-planar. I have 3 bonds that are actually in the same plane, and that creates a lot of steric strain, and so that's something that we're going to be messing around with. So steric strain means that we're trying to put something in the same place, and then overall, remember, steric strain gets worse when we make things bigger. And so in this case, this is the best possible situation. Hydrogen is the smallest thing that we can attach to something. So right now, this is the least sterically hindered that we can have. And we'll talk about, well, how do I make that worse? But just remember the transition state. One of the most important things you're going to get from this is that these 3 bonds that are not being involved in the reaction, for a briefest a second, when we're talking about the halfway point, they are in the same plane, and so they are interacting with each other. So yeah, let's run through this. Transition states roughly between the reactants and products. My OC bond is partially in the process of being formed. My OCl bond is in the process of being broken. That's why they have these dashed lines. It means partial bonds. Overall, what's happening is the negative charge is being transferred between my oxygen and chlorine. So that's why there's a positive, partial negative charge attached to my oxygen and a partial negative charge between my chlorine, because the negative charge is being moved from one place to another. So what affects this transition state? And this primarily comes down to the fact that those 3 bonds are on the same plane. So there is the effect of having a violated octet, but that's going to be true despite how we change things with my electrophilic carbon there. What we're interested in is what can I do to affect the stability of my transition state as a whole. And it really comes down to the fact that those 3 bonds are in the same plane. And when we started, they were 3 hydrogens. And what we're going to do is say, well, what happens when we make the things coming off my electrophilic carbon larger? And the answer to that is things are going to become more sterically destabilized. The larger molecules being in the same plane are going to be destabilized. Remember, steric effects mean, or steric strain means, this comes from large things trying to occupy the same state, and it destabilizes. So when we looked at the original one, there was 3 hydrogens. That's about as good as it gets. But what happens when we start exchanging those hydrogens for carbon? So the strain that we get as we start getting larger groups attached to my electrophilic carbon, that's going to create strain. That's going to destabilize my transition state, and this is going to make my energy of my transition state larger, and that's going to cause my energy of activation to increase. So as I add carbon groups onto my electrophilic carbon, or onto my electrophilic carbon, as the number of those carbons increase, that strain of that transition state where the three bonds are in the same plane, if I start replacing hydrogens with like methyl or ethyl groups, the steric strain is going to become worse. As the groups get larger, the steric strain gets worse. And as the steric strain gets worse, the molecule destabilizes, and then that causes my energy of activation to increase. And with an increase of energy of activation, the rate decreases. So energy of activation represents a energy barrier that I got to get over to go from reactants to products. Well, if that energy barrier gets larger, my rate decreases. So once again, this is something we talked about in 115, but this is really all that I want you to understand. As I start adding carbons onto my electrophilic carbon, the rate decreases. And we're going to find out this has got to have an overall effect on our understanding. So really what we need to talk about now is our designations for hydrogen. So remember primary, secondary, and tertiary. So we've talked about primary, secondary, tertiary, and quaternary carbons. We talked about the same things with alcohols, and we're going to do this a few times. But what we need to do now is talk about designations of halogens. Remember, halogens are going to be our leaving group, and this is the way that we're going to think about things in terms of how different electrophilic carbons are affected by my substitution reaction. So with designations for halogens, remember it always has to do with the number of carbons attached to something, and then that something can kind of change. And so with halogens, the designations are very much like what we had with alcohols. So for a primary halogen, just like a primary alcohol, we are saying how many carbons are attached to the electrophilic carbon. The electrophilic carbon is the carbon that's directly attached to my halogen. So we're saying how many carbons are attached to this one. So if I'm attached to one carbon, this is called a primary halogen, or you can even call it a primary leaving group at this point. Same thing here, the carbon that's directly attached to my chlorine, it's attached to two carbons, or secondary. Here, the carbon attached to my chlorine, or the electrophilic carbon, is attached to three other carbons, tertiary halogen. And here we're going to see one other thing. We didn't see this so much. If I don't have any alkyl groups to it, it's called methyl. And so we get into this case because this is kind of the best case scenario, especially for SN2 reactions, that this is going to produce the least amount of steric effects. I have no alkyl groups attached to my electrophilic carbon, the carbon that's directly attached to the chlorine. I have none of them. And so this case is called a methyl. So you can see this, it's just a CH3. So the idea is you can kind of infer this, that the more alkyl groups that I attach to my electrophilic carbon, the harder it is to undergo an SN2 reaction. So the harder it's going to be to undergo that transition state, the more alkyl groups I have, the transition state's going to become more sterically hindered. And so this shouldn't be a big surprise when we look at the rates of SN2 reactions. If I just generalize it and say, you know, what's going on, what's going to be the general rate for SN2 reactions between tertiary, secondary, primary, and methyl halogens, yeah, the tertiary halogen is going to be the slowest because we have three alkyl groups coming off of our electrophilic carbon. When we form our transition state where these three bonds are in the same plane, it's going to be very sterically hindered. Likewise, on the other end, with the methyl halogen, when we form the transition state, these three bonds are in the same plane, these three CH bonds are in the same plane. Hydrogen is the smallest thing that we can have, and so the transition state's going to be relatively more stable. So it makes sense between these, tertiary is going to be the slowest, or tertiary halogens are going to be the slowest reagents for SN2 reactions, and methyl are going to be the fastest. And so when we look at the relative rates, methyls go 30 times faster than primary. So that's the idea. This is relative rates of things. Methyl halogens react during an SN2 reaction very, very quickly. Primaries do it, secondaries it's kind of slow. And then the thing that's important now is tertiary halogens cannot undergo an SN2 reaction. So that's the idea. This transition state of tertiary halogen is actually so sterically hindered, the reaction won't occur. And so this is going to be important that, you know, tertiary halogens don't do this. So remember, just remember the individual bits, and then we're going to compare, contrast, and we're going to put all this stuff together. But this is the primary thing that we're looking at, is how does each one of these reactions affect the different type of halogen that we're looking at. So for right now, SN2 reactions go very quick with methyl. They go not at all, zero with tertiary halogens. You can't do an SN2 reaction with a tertiary halogen. And so this is something that we're going to be building off of. Okay. With every reaction, there's going to be a ramification. By that I mean every reaction has certain little quirks that you need to consider. And later on, we're going to put these all together, and the big question is going to be what reaction's occurring. But when you find out what reaction's occurring, you need to take a second and say, do I need to consider some of these kind of quirks that these reactions have? So the quirk with SN2 reactions are they undergo what's called an inversion of stereochemistry because they do what's called backside attack. So backside attack means that this molecule needs to be orientated just right. In order for the SN2 reaction to occur, the nucleophile needs to be coming on the other side of the carbon from the halogen. So what happens is it's actually called electron push. It literally does this. These electrons come in and hit the carbon, and they push the bromine off. So the incoming nucleophile attacks from the opposite side of the halogen. And then what happens is, in doing this, this pushes the other bonds in an opposite way. So they describe this like when your umbrella kind of unfolds or flips over inside of a windy day. If you look, these bonds are kind of pointing to the left. When the nucleophile comes in, it causes these bonds to flip to the other side. So like here, this hydrogen is pointing to the left. Now it's going to be pointing to the right. And overall, what this causes is a inversion of stereochemistry. So we'll take a closer look at this. But the idea is if this molecule was, say, S or R, it's actually going to be the opposite. So if this molecule was, let me look at it. As if this molecule is R, so this is 1, 2, 3. It's going in the right-hand manner. So this stereocenter that we have here, so 4 different things attached, this stereocenter is R, but after the reaction, it's going to go 1, 2, 3. It's going to be going S. That's what we mean by inversion of stereochemistry. So we'll look at some better examples of this just 1 second. But the 2 things you need to remember about an SN2 reaction, you get backside attack, so the incoming nucleophile is attacking from the other side as the halogen, and then we do a stereochemical inversion. So if I start with stereocenter this R, what I'm going to end up with is a stereocenter that is S. So for you guys in this class, I have to admit it's a little hard to see this, and you can kind of see why there's an inversion. The idea is when I'm starting, these bonds were pushing to the left. During the transition state, they're flat, and then when I push off the bromine during this, these bonds are going to be kind of pushing to the right, and it's very much like an umbrella blowing open inside of the wind where it inverts. What I like to do in class, and especially on exams, I like using a ring because it's a lot easier to see what's going on inside of a ring. So inside of here, for right now, just trust me, this is an SN2 reaction, and we'll talk about later how do I understand that. It's a lot easier to see these stereochemical ideas of inversion of stereochemistry in a ring. So remember, when we were talking about rings, rings have a defined upper and lower side. So when I look at my carbon here, The methyl group and the bromine are both on the upper bond, so they are on the same side. And my nucleophile now, so remember this is a carboxylate, this is kind of the basic question when I do the substitution, which means I'm going to be kicking out the leaving group and replacing it with my nucleophile. Is my nucleophile going to be cis or trans to my CH3 inside of this ring? So this is a lot easier to look at because there's a defined upper and lower bond. So the idea is, once I figure out this is SN2, I understand it's going to be a backside attack. So the nucleophile needs to come in from the bottom. That's what backside attack means. So the bromine's going up. My nucleophile needs to come in underneath. And in doing that, this hydrogen is pointing down. In the product, it's going to be pointed up. So that's the idea, is if these two groups are cis, after I do the substitution, the methyl group and my nucleophile are going to be actually trans. So because of backside attack, it's going to come in from underneath. It's going to kick out my leaving group. And now because the hydrogen was pointing down, it's going to kind of undergo this inversion. Now in the product, it's going to be poking up. And in my product, the methyl group and my incoming nucleophile are going to be trans. And just really quickly here, remember, even though we're talking about a carboxylate, the same basic steps occur. I kick out my leaving group, I replace it with my nucleophile, the negative charge gets transferred from my oxygen to my bromine. So in my product, my oxygen no longer has a negative charge, and in my bromine does. So you just literally draw a bond between my nucleophile and my electrophilic carbon, and then just cut off the bromine, and then you end up having your product.